Let's take a quick look at how learning switches work. A learning switch maintains a table between destination addresses and output ports on the switch, so that when it receives a frame destined for a particular place, it knows what output port to forward the frame. Initially, the forwarding table is empty, so if there's no entry in the forwarding table, the switch will simply flood. Let's look at a quick example. If host A sends a frame destined for host C, then initially the switch has nothing in its table to determine where that frame should be sent, so it will flood the frame on all of its outgoing ports. On the other hand, because the frame has a source address of A and arrived on input port 1, the switch can now make an association between address A and port 1. In other words, it knows that the host with address A is attached to port 1, so that in future, when it sees frames destined for host A, it no longer needs to flood, but can instead send the frames directly to port 1. So for example, when C replies with a frame destined for A, the switch now has an entry that tells it that it doesn't need to flood that packet, but instead can simply send the packet directly to the output port. Note also that when C replies, the switch learns another association between address C and port 3. So future frames destined for host C no longer need to be flooded either. They can simply be forwarded to output port 3. So in summary, if a learning switch has no entry in the forwarding table, it must flood the frame on all outgoing ports. But otherwise, it can simply send that frame to the corresponding output port in the table. Note that learning switches do not eliminate all forms of flooding. The learning switch must still flood in cases where there's no corresponding entry in the forwarding table, and also these switches must forward broadcast frames, such as ARP queries. Now, because learning switches still sometimes need to flood, we still have to take care when the network topology has loops. Now, most underlying physical topologies have loops for reasons of redundancy. If any particular link fails, you'd still like hosts on the LAN to remain connected. But let's see what happens when the underlying physical topology has a loop. Let's suppose a host on the upper LAN broadcasts a frame. Each learning switch will hear that frame and broadcast it on all of its outgoing ports. When that broadcast occurs, the other learning switches that are in the topology that contains a loop will hear the rebroadcasts. They, in turn, will not know that they shouldn't rebroadcast the packet that they just heard, so each of those switches will in turn rebroadcast the packet on their outgoing ports. And of course, this process will continue, creating both packet loops and what are known as broadcast storms. So cycles in the underlying physical topology can create the potential for learning switches to introduce forwarding loops and broadcast storms. So we need some kind of solution to ensure that even if the underlying physical topology has cycles, which it often needs for redundancy, that the switches themselves don't always flood all packets on all outgoing ports. In other words, we need some kind of protocol to create a logical forwarding tree on top of the underlying physical topology.